As you can see from the title, I will be talking about spin glass dynamics, and there will be a flavor for the AIMO people and AIMO experimentalists in the audience. And the work has happened to be simultaneous, although not coordinated, with the experiment by Benjamin Lev on exactly the same topic. So we came out basically a few days of distance, and then gonna try to review a little bit what they also did there. And I should start by acknowledging my collaborators, in particular Hossein, that is a Garage student in Mainz and has done a really brilliant job to bring this to light. So maybe you in the audience don't care neither about ergodic dynamics nor about cavity QED. So perhaps we may start with a question that is of broad interest. So let's say that I'm gonna give you, if it moves, doesn't move. Oh, I had to say okay to the record. No, I think I had to say okay to the record. Yeah. Okay, I will have to do it this way. So let's say I will give you a generic interacting many-body spin system. There can be 1D, can be 2D, can have short-range interactions, can have all-to-all interactions, so may lose connectivity. And now I ask you the question. You look at the size of one of the spins, and I ask you how big versus small S has to be for the full system to behave mostly classical. And the question, just to connect you with what you know from basic quantum mechanics, is that as you all learn in the books, right, when you make S bigger and bigger, basically your spin trying to be classical. Quantum fluctuations will go down like 1/s, essentially. Angular momenta will start to commute. So the question is, what changes if you add to the single body picture dimensionality and fluctuations? And of course, the question is highly model dependent. And that's the question I'm going to show we can answer in these cavity QED experiments of Benjamin Lev. So let me start to give you two introductions. One is to spin glasses, and another one is to their experiment. It's quite weird to introduce spin glasses in Paris, but I'm going to try that. I'm going to try that in the German way. So I'm going to quote for starters a notable predecessor that I have in mind, Kurt Binder. Essentially, the idea in the most simple way is the following. Let's say that you have a even classical spin system, right? These SI spins can be +1 and -1. And they're going to try to play with the temperature to see what happens to the system. But now the system has interactions that are disordered. So this disorder, of course, when too big, may induce frustration. And when you lower the temperature, the spins may start to be in conflict with each other. So rather than choosing to be maybe ferromagnet or anti-ferromagnet, so giving rise to standard form of order, something weird may happen. And that's roughly the basic picture that is behind the idea of spin glasses. So when you lower down the temperature, what is going to happen is that you are not going to order in the way you learn in traditional stat math books, but basically spins will start to be frozen. So we start to be in configurations all frustrated from each other, and they will have a slowdown, a critical slowdown or relaxation. So is more a change in the relaxational properties of the system in the dynamics rather than looking for order parameter. In fact, you can talk about a spin glass only if the global magnetization of the system is 0. And to make the picture a little bit more clear, that's what you know about free energy. When you have an Ising transition, you're going to spontaneously break it as you lower the temperature into minima. The common, let's say, idea in spin glass is that when you lower the temperature, you're going to have a ragged energy landscape. You're going to have an exponentially large number of minima in the system size. These barriers would be very large in system size and will prevent essentially you from finding the true minimum of the system, if any. And so basically you're going to be stuck somewhere and you will have a very hard time to relax. And if you try to zoom in this picture from above, that's roughly what you can expect, if you like, in phase space or in configuration of magnetization. Maybe in some of these minima in this sub-island, you may try to be ergodic, but then you're going to have these barriers. If you look at this from the top view, that are these darker gray regions that will be quite big and essentially will obstruct global relaxation. So maybe you're going to tunnel, you have a chance to tunnel, but then, you know, you have to explore the whole phase space. So even if you tunnel here, then maybe that's not your true minimum. You have to go somewhere else. and eventually you will essentially never reach the true minimum. So you're gonna get in astronomically long timescales ergodicity, and that's the common or popular idea behind glasses. And sometimes people want to credit Paris Nobel Prize with spin glasses. I don't know, let's say, what's the consensus about it. It would be fun to know what people say in Paris about that. But in any case, it's the selling line that at the moment most of us use when we give this talk. So why do you care? They were introduced in context of solid state in the 50s, right? But basically, it's pretty clear that they connect to fundamental questions on ergodicity breaking, and their real applications is not just fun words to many other fields of science. I don't have the time to go through, and maybe not even the expertise. However, the point is that now I'm going to show you a cavity QED platform where you can do very cleanly the simulation of dynamics of spin glasses. And you do that without the imperfection disorder of solid state. You do it with a level of control that is the typical narrative of cold atoms, but perhaps most importantly, you're going to do that tuning the size of the spin. And that's what I'm going to tell you now, and the way I'm going to connect it to my first question. All right, so now I'm going to, let's say, oversimplify the platform in Stanford. I'm going to tell you first the way I imagine it, and I'm going to give you a Hamiltonian in the next slide, so you have to be patient. And I will give you a few disclaimers about what truly happens in the experiment to avoid misguiding you. So essentially, the idea is that you have dipole optical traps called tweezers, optical tweezers sometimes, that are very strong focused light beams that can hold a bunch of atoms in a given point. And inside of the cavity, spare how this happens, these blobs that contains a tunable amount of atoms that are these blue arrows can all talk to each other via these green lines that are the photonic modes inside of the cavity. So the cavity can support plenty of photonic modes. They are all degenerate in the setup that they have there, and they are their old ways that connect these clumps of atoms. And you can control how many atoms. Let's say you go for a two-level description. So these are spins. So basically, depending how many you place, you're going to have here a big spin or a small spin. That's roughly what's going on. And these cavity modes have their profile, their, let's say, wave function profile. This is going to be highly space dependent, and is going to introduce inhomogeneous interaction between these clumps of atoms. So by glossing over for a moment how this looks like disorder that I will touch upon at the end of next slide, effectively what the photons are doing is that they are mediating a disorder interaction between these big spins. It's fully connected, so there is no notion of dimensionality, or it's an all-to-all, if you like, model, and that's what you are going to have to deal with. Now, you see quickly how the original question comes in, right? And that's what you're going to address. So how, by changing the size of this big spin, you will be able to change the nature of the spin class in this problem, which to our understanding is also an open question from a fundamental level. And just to give you an idea of the key control parameter in the problem, I mean, there are plenty, but one key control parameter is the ratio between the number of cavity modes and the number of these atomic clumps. So eta, that is the ratio, has to be above a certain threshold. If you don't have enough number of cavity modes, you won't have enough paths to connect all these clumps of atoms. You will not be able to sufficiently to frustrate in a sufficiently efficient manner the system, and you will not develop spin class. So in actuality, what happens in the experiment is a little bit different, but the essence remains. So what these people have is that they have 8 clumps of atoms. The number of degenerate cavity modes is of the order of 1,000, so you're all good. And what they do is that they pump light to bring the atoms above the superradiant transition. So this big spin S is actually a condensed BC that will give you a sort of XY frustrated spin system. And what they do is that they prepare always in the same initial condition. They quickly cool it down. It's actually non-equilibrium, so it's not, let's say, you lower the temperature like annealing, and they end up finding 4 most likely final configuration of spins. They start to look at correlations between these final states. They connect it to replicas, and they start to talk about quite complicated spin class theory to argue that they are seeing through the spin class. I don't want to discuss about what they see in the experiment. I wanted to make the point that there are differences with what I'm presenting here. And so, because I guess people like to see Hamiltonians, let me try to put in formulas what I said in words. So I'm going to be dealing at the end of the day with a disordered many-body spin boson model. So this is the bunch of cavity modes that are degenerate. And here you're going to have your spins 1/2 with two indices, one for I that is labeling the various clumps of atoms, and another lambda that tells you how many you have in each of these nodes. And this is the tuning parameter I'm going to play with. And interactions are going to be of the type XX, so X operator for light, X operator for the spin. They are going to be disordered. They are going to have zero average. And the variance that, let's say, is going to be G, non-zero. And that's a model that people have beaten to death since 2011, when there was the idea that this type of multimode cavity QED could realize spin classes. I'm going to give you a very short survey of what people have done before. But people are, let's say, circling around this model since a while. And I'm going to try to discriminate what we are doing, what people have done. But this remark is to say that is, let's say, an established modeling, at least qualitative modeling for what they do in Stanford. We are going to have photon losses. That's the only dissipative ingredient I'm keeping in, and I'm going to argue that is the only interesting one to have, in the sense that it can change the physics. Other dissipative channels are there. You have to have them small, otherwise they're going to screw up everything. So photon losses will be a key player, or at least for modeling the thing. And so, of course, you're going to ask me, right, how can I start to get intuition about it before doing calculations? So one thing that quantum opticians like to do is to imagine the limit in which the mediator of interaction, in this case photons, are very fast. So their energy scale omega 0 is much bigger than the one of spins delta. And so they mediate a non-retarded interaction, and you can write down an effective spin model in a trade of the light matter or spin boson problem. And what you're going to find out is that there are going to be two interesting pieces in your Hamiltonian. You will get intra-cluster interactions, so interaction between the spins inside of the same cluster that comes with a G-squared term. So this thing is not going to be frustrated, right? Because frustration comes from sign changing in this coupling G. But inside of the same cluster, all the spins with the same index I are going to talk in the same way with each other. So this big SI now is the sum over the various blue spins inside of each block. And this guy, you know it, it's a fully connected IC model. It has a paramagnet to ferromagnet transition. There's nothing to talk about. But between clusters, you're going to have now a disordered, frustrated interaction. So there is the option for sign changing, because the G alpha I and G alpha J are different. And so this is the guy that is going to fight against potential ferromagnetism to generate spin clusters. And notice that G is the guy that will give you traditional ordering, ferromagnetism, and possibility of spin class. So it's not obvious what is going to happen, right? But notice that the size of the spin enters in both expressions. So there is room for trade-off. Now, in the Stanford experiment, if you care, disorder comes from the fact that you are summing over the effective interaction that contains, let's say, the 100 photonic profiles inside of the wave function profiles of the photon inside of the cavity. And the sum results in something that is not spatial translational invariant, that is fastly sign changing, actually controlled by omega 0, that is the waste of the fundamental mode. And so that's in actuality what's the source of highly sign changing, not spatially translational invariant interaction in the experiment. Now, maybe this comment will come completely transparent to you, but like quantum opticians care to know if you solve the problem when the photon is in jargon active, or when the photon is just very fast, is passive, and is instantaneously mediating interaction. We don't do that. We solve the full light matter problem, and because I'm talking to a, let's say, theory-versed audience, in the end of the day, perhaps the fact that we can do nice things like long time, thermodynamic limit, play with spin length, maybe it's not so surprising because it's fully connected. So after disorder averaging, being a model without dimensionality, by, let's say, oversell or underselling, perhaps what we are doing is a sort of dynamical midfield. So the fact that this can be done in full glory, perhaps to this audience, is not surprising. I will not talk about it. That's the elephant in the room. I will not tell you how we do this concretely, because there is no time, and I think physics should come first. So, all right, what you should expect. So in summa, just to summarize, right, there are two tunable parameters, level of frustration, so how many paths you have to have this sign-changing interaction to reach all the clamps in the game. This is eta. And then you have G, that is the strength of these interactions. And I guess we all agree, small g, small eta, nothing. Small g, large eta, still nothing, because this guy is not strong enough. And you have to be careful when you correct G, because of course, if you can't frustrate efficiently, you're going to end up into a ferromagnet, having this guy win. That's where people have located the spin glass in the past. And basically everything started with phenomenological argument or saddle point calculation. Later on came exact numerics on small samples. I think it really took more than 10 years to realize the experiment. Now I'm going to, let's say, argue the dynamics in the model is way richer. And somehow we are indeed the first doing that for tunable spin and very large samples. So numerics on small samples that came basically last year, or at the same time actually in which we put out the paper, is the direct competitor. Now, what we are going to see, we want to form the spin glass. So we are going to do something that you folks like a lot. In StatMech, we are going to do a quench. We are going to start in a certain state that is very boring. So the photon is in the vacuum. All the spins point in the same direction. So you have a spin coherent state. And you're going to evolve your system with parameters of this putative spin glass transition that people have located before by qualitative means. And this is perhaps a remark that I don't need to do at the moment. So let's look at dynamics, right? So this is what we get from our non-equilibrium diagrammatics. And at the moment, we will start looking at something simple that is not enough for spin glass, but is necessary condition. So how magnetization goes down. If magnetization doesn't go down, there is no reason to talk about spin glass, right? So that's the cartoon as a function. The number of spins in each clamps is going from deep quantum 1 to classical 1000. And you see essentially that what happens is that when NS is sufficiently large, the inter-cluster interactions, so the interactions for the spin inside of the cluster that are LMG, are going to win over. They're going to stack you around a sort of prethermal or metastable, however you want to call it, a ferromagnet. And only way later you're gonna be down to zero magnetization. This doesn't happen in the case in which an S is equal 1 or 5. You quickly go to an X equal to 0. So that's a first indication of different, let's say, dynamical stages of relaxation in the problem. And there is another reason for showing you this plot and to convince you that we are not nuts. So why don't you do something simpler like semi-classics to study the problem while you have to beat yourself with diagrams, right? And that's what you will get with discrete truncated Wigner, which is semi-classical phase space method. The blue line is our theoretical approach, and this is going down to the supposed quantum limit, by supposed because semi-classics cannot get there. So all the curves look identical to each other, and basically you don't see this quick and big bump of going down quickly to 0 for MX in the quantum case. So basically semi-classic doesn't show that. And so this is to give you a small hint. What the diagrams are doing are resembling 1 over S corrections in a most convergent and efficient manner. And this is my only single note about the manner. All right. So spin glasses are more, and perhaps even more than aging. But that's the best I'm going to convey to today. So I'm going to convey to you today aging and a little bit of Edwards and some other parameter, and then I will leave for discussion on later other signatures. So I will keep a phenomenological approach if you want. A proxy of spin glasses is aging, which is a very sophisticated manner to remember initial condition. So this is what is going to happen. We are going to measure correlation functions. We are going to do that at 2 different times, and we are going to play with these 2 times. So tau is the time after the quench, and I'm going to split the moment in which I measure spins in 2 clumps of atoms by a small time t, all right? So that's the object we are going to look at, so you can appreciate the order of average, I'm sure you care. And we are going to look at spin glass when Mx has gone to 0. US spin glass is basically at very long, small times. So doing 2 measurements and separating them at very long times, you remember what's going on. So your correlation time is non-zero. And people sometimes call this the spin glass order parameter or Edwards-Anderson order parameter is connected to deep spin glass theory, but there is not the time to go through, and it's not even probably the point. All right, so for people that don't know what I'm talking about, actually there is more. So the reason why you call, what I want to show you is called aging is the following. As the system gets older, so as you spend more time tau after the instant you did the quench, the system is gonna relax slower. It means you're gonna see curves, and it's gonna have a very slow decay with small t. And so that's basically the way it should look like. So the spin glass regime, trust me, this is a quench in that condition. As you send tau to larger values, that means going from yellow to darker purple, is gonna have a weaker dependence on t. So the more time passes after the quench, after the system is aging, and the slower is the relaxation. But the paramagnet doesn't show that, right? All the curves are on top of each other, they decay with large t, and it doesn't matter how old they are. And what you can ask in this context is, again, how this entire business will depend on spin size. And you are gonna see here essentially that going again from yellow, that means semi-classical, down to quantum, you are gonna have essentially a completely different decay with small t. So you have a slow decay for large spin, and you have faster decay for small spin. So actually fluctuations here are somehow weakening aging or fighting against spin glass order, which perhaps makes sense, right, in a picture of tunneling between the minima that I was giving you at the beginning. So we are now in a position to answer our question. Right? When the system is quantum, where is the quantum to classical crossover? That's a question in general very hard to answer, right? You do it phenomenologically, you wave your hands. So you look at the spin glass order parameter, and basically what you observe a long times is that roughly already around spin order 2 or 3, I don't think it really matters how you locate this quick crossover. It looks identical to what you will get for S equal 1 trillion. So basically in this system, you become classical if you want to push it and be provocative as spin equal 3, if you want. That's the quantum to classical crossover in this fully connected spin glass model. It's something you could do in the experiment. You could basically load very few spins. We can discuss how to do that later, and compare it with what you're gonna get with very large S, that is what at the moment Ben Lab is doing. So that's why we were quite excited. It's, I think, one of the few cases that I know. I'm very happy if someone can bring me something different in which an interactive model with plenty of fluctuations and enough complexity, you can quantitatively locate the crossover, not to do phenomenology, not to do, let's say, end wavy arguments. And perhaps because I made the comment right at the very beginning that photons are important in what we are doing, you can also ask another question, how the spin glass order is weakened or not by active photons. That's a question that makes little sense in solid state, right? In solid state, you have photons. Photons are there, they have their energy scales. You don't control them. They do what they do. But in cavity, of course, you can play with the energy of these photons. It happens by a sophisticated detuning of the light, of the lasers that drive the atoms. I don't think for the audience it's important to know that. And the point is that, of course, when you're gonna have photons that have very large energy, so they are mediating virtual exchange between the atoms, you have the spin interactions that I was giving you before. And now when you start to reduce their energy, they may become very resonant with the atoms, right? And typically in perturbation theory, the interaction between spins goes down as the inverse of the energy of the mediator. So on one hand, you may think that's cool. This is going to enhance the interaction between the spins. It's going to make spin glass order stronger. But at the same time, when you're close to resonance, you're going to exchange real photons. And of course, this is going to give you a lot of heating. They're going to give you intrinsic dissipation between the atoms and the photons, not coming from losses into the outside. Internally by the system starting to act as its own Beth. And what is nice to see is that the model show you that in fact who's going to win is this naive perturbation theory scaling. Of course, the scaling is not exactly just 1 over omega c, but the point is that heating is not taking over. At resonance, you have a bump in spin glass order parameter. That's the real comparison. So that's essentially what you're going to see in the actual calculation. This was a cartoon to convey the idea. And here I'm doing it at different photon losses. One of the reasons to show this at different photon losses, that's something I haven't told you, but I think it's important for you to know, is that photon losses are helpful to cool down the system. So there are initial states in the paramagnet you can prepare. They are very energetically respect to the Hamiltonian of spin glass, and they are going to melt spin glass. So if you start with a state that is very energetically, you're not going to see spin glasses. But if you start from the same state and add a little bit of photon loss, not too much, otherwise you overdamp, this is going to suck out energy and it's going to pull you down more efficiently into the spin glass. So photon losses help. I mean, everybody that has done calculations on quenches of spin systems knows that, right? That you can melt order when you start from very high energetic conditions. And so this is my summary. Why do care? So why we should care at all, right? Okay, there is the usual narrative on quantum simulators. I'm sure you are very tired to hear that, so I will let you read it. But one thing that I think is very nice in these AMO platforms is that you can start to think ways to tune the range of interactions between clumps of atoms. And this is a big deal for people doing spin glasses, because spin glasses are very well known for fully connected cases. A lot of models that allow us to understand spin glasses is for fully connected. Basically, no one knows, I'm happy to learn if you think differently, what happens if you have short range interactions, disordered, we do have still spin glass or not. Then we can give you a chance to get there. And there is the item of tunable fluctuations and the role of dissipation to cool down and form the spin glass that's still there. And for me, from the fundamental point of view, this is one of the few cases that I know where you can work out concretely this quantum to classical crossover. And so with that, I am down. There are other signatures. I let them here for your questions or for further discussions. Thank you.
Yes, I have a question about your provocative statement that the quantum to classical transition is a spin free. Do you say the thinking that it's valid only for this specific model, or in your mind this is more general and would apply in any problem when I change the speed?
Of course, the conservative answer is that applies only to this model, right? So the way I will not get butchered all of a sudden is to say, oh, it's very model dependent, depends on dimensionality, fluctuations. In actuality, in a bunch of simulations you do for other systems, and you do truncated Wigner, for instance, and you try to compare with other methods when you can, the transition to classical happens quite fast. So of course, the threshold 2-3 is super dependent. But like if you ask me, you believe it happens at 50? No. I believe it happens way down, and there are some papers we can look at them together where you compare truncated discrete, truncated Wigner with other methods. You see the crossover there. So,
but it depends what you're looking at. I mean, it's not for spin transport. Then you also have a spin classical duality, a spin one-up. Doesn't mean. I mean, it's a matter of what you look at.
It depends what we call quantum to classical, yes, right? Right? It depends what you call. Here is for the purpose of talking. Do you have a different spin glass of that parameter, yes, right? Exactly. Another question we may ask that I find very difficult, and I'm happy for some experimentalists as ideas, is, of course, the spin glass is the same, right? But is there a way to know about quantum coherence? Maybe quantum coherence is still undergoing a slower crossover. And for the sake of the phase transition, doesn't matter. But if I'm interested in knowing how much the system is still quantum correlated, perhaps this is happening at something else. But I don't know a way to measure.
No. You didn't say much on the kind of technical part, but are you at the end using some high spin techniques to calculate the small spin results? I mean, what are your maybe?
I'm sure this is the only place in the world, if any, where someone would have asked me to show my backup slide that I never show when I do this talk, right? So I think it's very similar to what some guy was talking about. No, actually, it is the talk by Nahum at the beginning. So the way you have a large spin is that you have many copies. So you represent spin 1/2 as Majoranas, and you have several copies. He was calling them flavors. And that's your control parameter that allows you to do exam infinite diagrams. That's the way in which your convergence, putative convergence to small spin is going to work out. Did I answer? No, from the phase I haven't answered. I thought it would.
Okay, let's thank Jamil again.